In this video, we're going to have a look at some first-order differential equations that involve related rates. So let's start now with a conical tank. It has a radius length at the top equal to its height. Okay, now my diagram here is a little bit misleading because the idea is meant to be that the tank is a very sort of flat one. If I were to draw it like this, it'd be more something like this, because we want the radius here to be equal to the height. Okay, so it's something along those lines. So a very short, squat conical tank. All right, now water initially at a depth of 25 centimeters leaks out through a hole in the bottom of the tank at the rate of 5 times the square root of the height, cubic centimeters per minute. So it's the volume of the water coming out, where the depth is h centimeters at time t minutes. Okay, so the water's leaking out through a hole in the bottom of the tank at the rate of 5 times the square root of the height, cubic centimeters per minute. Okay, what we want to find is dh dt as a function of h and to solve it. That's our first thing. And then part B, at what time will the tank be empty? All right, well, we know that the volume of the conical tank is 1/3 pi r squared times the height. Okay, and we have the situation here that at the top we have r is equal, the radius is equal to the height. Okay, hence that little short squat diagram over here. And so we can substitute where r is, we can put h in instead. So we go put an h in where the r squared is, so we have h squared times h, so we'll have the volume is 1/3 pi h cubed. And we also know from related rates that the rate of change of the volume with respect to time is equal to the rate of change of the volume with respect to height by the chain rule times the rate of change of the height with respect to time. Okay. Now we have that dv dt we were given is 5 times the square root of h cubic centimeters per minute, and we take that to be negative because the volume is decreasing. It is a decreasing rate, so we have a negative value. And from this equation here, we can see that dv dh, if we differentiate v with respect to h, we're going to have pi h squared. Okay. Now, from this relates over here, where dv dt is, we can substitute in minus 5 times the square root of h. Where dv dh is, we can substitute in pi times h squared, and then we're left with dh dt. And we wanted to solve for dh dt as a function of h. So next line down, okay, we now dh dt, if we rearrange this, will be minus 5 times the square root of h over pi times h squared, and simplifying this, dh dt is minus 5 on pi times h to the power of 3 on 2. Okay, we can solve it. We can take the reciprocal here. dt dh is minus pi on 5 times h to the power of 3 on 2, and if we separate the differentials as we normally do with our technique here, to separate them and put the t's on one side, dt on the left, and all h and dh's on the right. Okay, then we integrate both sides, dt, and what we have is the integral here minus pi on 5 times h to the power of 3 on 2 dh plus the constant of integration. Okay, well that gives us t equals minus pi on 5 times h to the power of 5 on 2. We've increased it from 3 on 2 to 5 on 2, increased by 1, divided by the new power, 5 on 2, which means we take the reciprocal of it, so the 2 ends up on top, 5 underneath, and that leaves us with t equals minus 2 pi over 25 times h to the power of 5 on 2 plus c. Okay, it was just convenient to differentiate it that way, to anti-differentiate it that way, sorry. And next thing we can do, let's subtract c from both sides. That gives us minus 2 pi on 25, h to the power of 5 on 2. Okay, well, let's multiply by 25 on 2 pi minus out front. And that gives us h to the 5 on 2. And tidying that up, we can multiply through the minus 1 there, so we get 25 on 2 pi. C minus t is equal to h to the power of 5 on 2. And if we then we raise both sides to the power of 2/5, okay, if we do h to the 5 on 2 all to the power of 2/5, we're of course going to end up with h, and so we get h is 25 on 2 pi c minus t to the power of 2/5. Okay, so that's the height at any particular time t. That's the general solution. We haven't solved for any particular solution. Okay, we can do that now because we did know that at time t equals 0, the height was 25 centimeters. So we can now use that information to find the particular solution in this case. Let's just scroll down here. Yep. So here, where the h is, here we're going to put in 25. Where t is, we're going to put in 0. Okay, so here we are. Okay, that implies that 25 is equal to 25 on 2 pi c to the power of 2/5. All right, 25 to 2/5 is equal to 25 on 2 pi times c. Okay, rearranging c equals 2 pi on 25 times 25 to the power of 5 on 2. That's 2 pi on 25. Let's just play with some indices. 5 squared is 25 to the power of 5 on 2, so that's 2 pi on 5 squared. The 25 becomes 5 squared times here 5 to the power of 5. Okay, that gives us 2 pi times 5 cubed is 2 pi times 125, so it's 250 pi. So our particular solution becomes h equals 25 on 2 pi, 250 pi for c, this c here, minus t, all to the power of 2/5. Or if we express this in terms of t only, we would have t as 250 pi minus 2 pi on 25 times h to the power of 5 on 2. Because you remember, okay, we had up here, okay, we could express it that way. The c here is 250 pi minus all of this. Okay, so either way, so that gives us the particular solution. Okay, so the tank is empty when h equals 0. What is t? Okay, well, obviously when the height of the water drops to 0, the tank will be empty. So how long does it take to do that? Well, t is 250 pi times 2 pi on 25 times h is 0, 5 on 2. That gives us 250 pi minutes. That's approximately 785.4 minutes. Approximately 13.09 hours, or approximately 13 hours and 5 minutes. Okay, that's our first question. Let's have a look at another one there, different question altogether. And here we go. A balloon is being filled with air at the rate 150 cubic centimeters per second. So that's rate of change of volume with respect to time, because it's cubic centimeters per second. That's the rate it's being filled, so it's increasing. Assuming that the balloon remains spherical, at what rate is the radius changing when the radius reaches 3 centimeters? So at the instant the radius is 3 centimeters, what is its rate of change? What is the rate of change of the radius with respect to time? So we're given that dv dt is 150 cubic centimeters per second. We know that the volume of a sphere is, a balloon is a sphere, 4 on 3 pi r cubed, and we want dr dt. Okay, that's the first step, and then we can answer the particular question of what is the exact rate of change dr dt when r equals 3. All right, dv dt is dv dr by the chain rule times dr dt. Okay, now let's just invert that a bit, and rearranging it gives us dr dt as dv dt times dr on dv. Okay, now here dv dr is just the derivative of this, which is 4 pi r squared. Okay, and dr dv, the reciprocal of that will be 1 over 4 pi r squared. So dr dt is dv dt, okay, we know what that is, times dr dv. We have dr dv here, we have dv dt, which is 150. Dr dv is the 1 over 4 pi r squared. And so that implies that dr dt is 150 on 4 pi r squared. Okay, now, so we can find dr dt, we can find when the radius is 3 centimeters, at what rate is it changing? So we can substitute in here our 3 centimeters. So dr dt at r equals 3, dr dt is 150 on 4 pi 3 squared, is 150 on 36 pi is 25 on 6 pi when we simplify that down. And what we centimeters per second, so the rate of change of the radius with respect to time is 25 on 6 pi centimeters per second. Okay, how about we solve this and find at least a general solution? Okay, well, at this point now, what we might do then is from here, we might separate the differentials, okay, and what we get is we're going to have, let's put the r squared dr together, and then we will have 150 on 4 pi and dt over here. Okay, so that's what we're doing here. And then what we're going to do is integrate both sides. Put the constant of integration on the right there, so the integral r squared dr is the integral 150 on 4 pi dt plus c. That gives us r cubed on 3 is 150 on 4 pi times t plus a constant of integration. Why don't we multiply through by 3, so we get r cubed is 3 times 150 on 4 pi times t plus c in parentheses. Okay, well, expanding that out, we have r cubed is 450 on 4 pi times t plus 3c, and we're just going to tidy up that 3c and just call it some other name, give it another, call it k. So 3 times c is equal to a new constant k, just to tidy things up a bit. And then what we're going to do is take the cube root of both sides. So r, as a function of t, is 450 on 4 pi times t plus our constant k, all to the power of 1/3. So this gives us the radius at any moment in time, where k is still an unknown constant because we've only derived the general solution here. We haven't gone for a particular solution, but the general solution has that form. Just depends on initial conditions or boundary conditions to determine what k is. One last example, a different type altogether, but again involving related rates. So we have a particle moves along the curve with equation y equals 2x cubed plus 1, so that its velocity parallel to the x-axis is kept constant at 5 units a second. Because that's quoted as velocity and is appropriate to quote it as velocity and not speed. The speed is 5 units per second, but because we're given also a direction, the x-axis, okay, it's appropriate to call this the velocity because we're given both a speed, 5 units a second per second, but we're also given a direction, so that makes it a velocity. Otherwise, we'd refer to this as a speed if we weren't talking about any directions. Okay, now find its velocity parallel to the y-axis at the instant when the particle passes through the point where x equals 2, y equals -1, and then finally we'll find y of t. We'll find the solution y of t if x equals 0 when t equals 0. Okay, let's start with part at the point x equals 2. All right, so the velocity parallel to the x-axis is dx dt. And we've been told that dx dt is 5 units per second. So we need to find dy dt, and we can do that through related rates. Okay, from the original equation up here, y equals 2x cubed plus 1, dy dx will be handy using related rates. Dy dx from here is 6x squared, so dy dx 6x squared. And now from the chain rule, dy dt will be dy dx times dx dt, because we know dx dt. And we also know, my pen's been a little bit sloppy there. All right. Okay, so dy dt is dy dx times dx dt. We're told dy dx, we've calculated here, is 6x squared. We were given that dx dt was 5 units per second, so 5. Multiplying those together, we get 30x squared. So dy dt is 30x squared. Now, if x equals 2, then the rate of change of y with respect to t, that's the velocity of the particle parallel to the axis, at x equals 2 will be 30 times 2 squared. Where the x is, we're going to put 2 squared. 30 times 2 gives 120. So the velocity parallel to the y-axis is 120 units per second. Okay, so because we want to find the velocity parallel to the y-axis at the instant when the particle passes through the point where x equals 2. So the instant where it passes through the point x equals 2, dy dt was 30 times x squared in general. At that point, that moment where it passes x equals 2, dy dt was 30 times the 2 squared, giving us 120 units per second. Okay, so that's the velocity parallel to the y-axis at the point where it passes x equals 2, that moment in time. What about where y equals minus 1? Now, if y equals minus 1, okay, so let's go back to the original equation. 2x cubed plus 1 is equal to y, and we'll put where y is minus 1. That tells us that 2x cubed is minus 2. Okay, x cubed is minus 1. Okay, dividing both sides by 2, x cubed minus 1, and the solution there is x equals minus 1, because minus 1 times minus 1 times minus 1 gives us positive, times a negative gives us minus 1. All right, then dy dt, okay, is 30 times negative 1 squared, which is just 30. Hence the velocity parallel to the y-axis is 30 units per second in the positive direction. We know it's a positive direction because there's a plus value here. Okay, also there was a plus value here too. Okay, what was part C? Now we need to solve for y of t. Okay, so we're going to solve for y of t. Now, we were told when we solved for y equals y of t that if x equals 0 when t equals 0, all right? So x will be 0 when t equals 0. Now we have dx dt was 5, remember, 5 units per second we were given. The integral dx is the integral 5 dt plus c, so x equals 5t plus c. Now, where c equals 0 because, now we're going to get 0 here because when t is 0, x is 0. So if we put 0 in here, 5, 0, 0, x is 0, c must be 0. We've got no choice. Okay, so that happens when x is 0, t is 0. Now we know that dy dt was 30x squared. Okay, and we've just found that because c is 0, our solution is x equals 5t. So from dy dx is 30x squared, which we found up here before, okay, where the x is, we can simply put 5t. So we have 30 times 5t squared. Okay, that's all of that there. So now we're going to separate the differentials again, and we're going to have the integral dy equals the integral of 30 times 5t dt plus c. Okay, and y equals 2 times 5t cubed plus c. Okay, t equals 0 means, now t equals 0 means y equals 1. If I put 0 in there, I've got y equals 1. Okay, x equals 0, y equals 1. Okay, so remember x was 5t. Okay, if that is all 0, then and y is equal to 1, that implies c must be 1. And so y of t is 2 times 5t cubed plus 1. All right.